How about now? Okay. All right.
Recording
The last line that I wrote on the board. Which topic? Which part of the SVM we did go through? So we mentioned that W or theta is perpendicular to the line or hyperplane. All right. So in the previous class, we discussed that the W or theta is perpendicular to the line or to the hyperplane that it belongs to, depending on the dimension, right? Did we talk about the distance of a point to a line or hyperplane? No. So now let's assume you have this line. It doesn't matter, line or hyperplane, just in 2D line. And then you have a point here, x prime or x1. So this is this line is W transpose x plus b equal to 0. This is the line. And that's W. How would you calculate the distance of this point to this line? Project it down. This one or this one? This one. So you project it here like perpendicular, right? So it's like you drop to the point. What's next? So these two are parallel, right? So let's call this point x2. So x1 minus x2, we said it's parallel to W, right? We also know that if this is parallel, that means x1 minus x2 is equal to some ratio of W. It's either larger or small, basically. From the other end, we know x2 is on the line, correct? Any point on the line has the equation of W transpose x plus b equals 0, right? So that means W transpose x2 plus b should be equal to 0. Because that's part of the line. So we have two things. 1, 2. So here we can rewrite x2 as alpha or x1 minus alpha W, right? And then we can replace that here. So we will get W transpose times x1 minus alpha W plus b equal to 0. Okay. And we are interested to find alpha. So we get minus b over W transpose x1 minus b or minus of that. Let's see. So this plus B over W transpose W. Right? So, which is norm 2 of W transpose X1 plus B. Norm 2. So, basically, anytime you want to calculate the distance of a point, so X1 minus X2 is alpha times a W, right? We know what is alpha, right? So basically, if you multiply it by W, that becomes the distance of that point to that line, right? So now this value, or the distance in general, the upper part could be positive or negative, depending on which side of the line you are at, right? So if there's a point on the right side, this distance is positive. If you're on the left side, the distance is negative. The denominator by default is positive, so numerator is either positive or negative. If we want to calculate the distance, we don't care about the positive or negative. We can just put modular around it. So it's just every time we have a positive, basically, distance. So
it should be like W square in the denominator, right?
so we need to multiply it by
W transpose W.
so this is what's going to happen. This is alpha, right?
Yep.
So you need to multiply alpha by W.
Okay, so one gets cancelled.
Right? No, you first need to multiply alpha by W, because the distance X, if D or the same X1 minus X2 is the distance, we say this is equal alpha times W, right? So if you multiply this by a W, you get a W here, right? That's one thing. But that's not still a distance, that's just a vector. If you want to calculate to a distance, what should you do? Calculate some sort of norm, for example, right? So if D is a vector of basically dimension, this minus the other one, you want a distance, you need to calculate D transpose D, and norm 2 of itself, because norm of a vector gives you the length of that vector, right? So if you multiply this by itself, basically, this upper W cancels out. So you will reach out to transpose X1 plus B over norm 2.
The denominator should be a square, right? Because W transpose W is a square.
Initially, it has to be square.
I see what you say. Yeah. So X transpose X, right? Yeah. So that's a square. But the this one basically will be at the end be what we do. That's correct. That's to the power of 2. Okay. So now we discussed two things. So we discussed perpendicularity of W or theta to a hyperplane or to a line, and also how to calculate the distance of a point to a line. But why we want to review this, let's go back to SVM. So what we mentioned, I don't know how much we went over with this SVM, so I will try to do a refresher. But SVM, we say that, so there is a class of classification that we're learning here, which has this idea that basically it says, we know there are a series of lines that they can separate two classes from each other. But among those lines, there's one line that's going to be the optimal answer that has the best separation. And the goal is to find that one. And SVM basically gives you that line. So we mentioned that for SVM. So first thing we are going to talk about is we're going to learn a linear SVM. It's binary. Class in SVM, it should be +1 - 1. Okay, that's important. We will see later. That means if you have a data set, if you want to pre-process it, first thing you do, convert class Y column to 1 - 1, not 0, 1. Okay. Now, this is class plus one, and let's say this is class minus one. So this is a linear separation. That's why again we will see a non-linear version, but we start with the linear version. That means that you cannot right now the version that we are learning you cannot apply to scenarios like this. If you have a classification like that you want such a decision boundary, that doesn't work. Okay. So we talked about that SVM. The main goal was that you want to find this center line. Right? That line is going to separate both classes from each other. We say that the best way, basically, let's break this down. So the best way to describe this is, let's assume I'm standing between two groups, right? I have a group on my right, group on my left, and my goal is that to find the best position to stand in between them, that has the maximum distance from both classes, right? So in order to do so, the way that this is just conceptual, translation. Imagine I just extend my arms, right? So as far as it can go, right? So the palm of my arm reaches to closest person into this group, and the other one is the other group, right? And now I'm exactly on the center. So by pushing these two lines to my hands to the corner, first things I did is that I tried to find the closest entity or the closest basically data point in each either basically classes. So that's the first thing that SVM does. By trying to find basically the closest data point to you on left and on right. If you know which one is the closest, like for example, you draw a line here, because again, the whole idea is that I have this line, I send it as far as it goes until I reach to data point on one class minus one. That could be either overlapping, going over it, or getting too close to it, And then I do the same thing for the right side. After I did that, because I have the both line and they are parallel, then I fit a line on the center of those two. By doing so, this line in the center is guaranteed to give you the maximum separation from either class. And that's why that's going to be the perfect line. But other scenarios, other algorithms that we saw, like for example, logistic regression, every time you solve, you get a different answer, different line, because at the end, it gives you perfect separation, but every time you get one answer, right? So this one is you're going to get one unique answer, and it's going to be the optimal among those ones, okay? Now, let's define something here called margin. Okay, so margin, the definition of margin is going to be the closest or the smallest distance between points and the line, basically. So now, let's look at these lines that we have. First line here, again, these two lines on the corners, we're not solving for those. Those are more like conceptual. The line in the center is what we are solving, right? But let's look at this. Assume this. We have this line, W transpose 1 X plus B1 equals 0. 1 stands for class 1. And then here we have W2 minus 1 X plus B minus 1 equals 0. So we have two lines, one for the class 1, one for class 0, right? And then the line in the center, we're going to call it WTP X plus BP equal to 0. It's the median among those two lines, basically. Now, when we're looking at the definition of margin, it says the smallest distance or the minimum distance among points and a line. So if we are looking at for class plus 1, and this line, which this line that belongs to class 1, this distance here is going to be M1, the margin for class 1. Because in order to calculate the margin, you need to calculate all these distances, basically, right? And pick the minimum distance among those, basically. So this one for class plus one is the minimum, is the closest data point to this line, right? Yeah, look at the example that I brought. If I raise my hand, the closest distance between the first person or the closest person and my hand, right? So that is the margin for class plus one. And the same thing here, it repeats. So this is the margin for class minus one. Okay. Now, if we want to define this margin, margin is basically a distance, right? And we define distance as this equation, correct? So technically M1 is W transpose 1 X plus P1 over, and then M2 or M minus 1, sorry, M minus 1. W transpose minus 1 X plus minus 1. Right? That's the distance between this point and this line, and distance between this point and this line, right? And then if you calculate this, let's say MP, which is, let's say this is the margin for this inner line. Right, this one also has a margin, right? And we know the margin for the line in the center by default is larger than the margin for the lines on the corners, right? So MP is greater than M1 and M minus 1. Okay, so all right, so now let's introduce something. Let's define margin as introduce a random variable, just a variable, not a random variable, a variable. We will say gamma of W and B, and this is going to be margin. Okay, this is margin. We're going to introduce it as margin. What was the definition of margin? The minimum distance among all points and a given line, correct? So when we are solving here in this SVM, the actual line that we are solving for is the line in the set, right? So also I will drop that P because, you know, technically there's no P, it's just W transpose X plus B, because we only learned one W and one B. So we are basically, let's draw it here. So we are trying to solve for this line, W transpose X plus B equal to 0. And these are the points in class 1, and these are the points in class minus 1. Okay. So when we are looking at the definition of margin, margin says that the minimum distance among points and the line, correct? So that means if I write this, it's going to be minimum I from 1 to n distances, you know, and we know the distance basically as W transpose plus B over among all points, the minimum distance basically. That's the definition of margin, correct? Now, remember one of the terms that we defined, I say that SVM has a couple of names like a street view classifier, SVM itself, and maximum worst margin classifier, right? Or maximum margin classifier. Now, let's understand that term, maximum margin classifier or maximum worst margin classifier. Why do we call that? If you if we are, let's say, we're interested to find this line in the center, right? And there are two ways we can look at this. Either, if let's focus first approach, look at focus on M1 and M minus, right? So my goal is that to push these two lines to the left and to the right as far as possible I can until I reach to the some points from each data class is correct, right? By doing so, I'm minimizing the margin, correct? Because the closer to the line gets to the points, the smaller the margin gets, right? So by minimizing the margin here, I am, what I'm doing here, maximizing the inner margin, right? So maximizing worst margin, right? So that's why we call it worst margin. Margins, we want to be small, but that one we want it to be large, maximizing for the inner margin, basically, right? So our goal at the end is this. You want to have this region, this internal region, margin, to be as wide as possible, right? And that means that you have a really clear separation from either class, okay? Now that happens in two steps, if you think about it. When the line, when you have these points, right, at the beginning, first thing is that you don't know, if I just put one line randomly over there, let's assume there's just one random line in the center, right? First step that you need to take is to solve for that given line from right and left. Find which points are closest to that line. Correct? That's the step one. So step one for a starting point, a random line, I will look at the right and say that which data point has the minimum distance to me. Right? That's a margin for the right and margin for the left. Right? Now, the step number two is that, okay, this line that you have is not optimal. So now you need to optimize the line. Right? Think about it kind of like if we just randomly write a for loop and then start iterating over different version of the line, different lines basically, and every time compare the distance, and at the end try to compare this line to see which one is the best. That's the idea that we have here, right? So there are two steps. One is that if I have a line, for this line, which points are closest to me? Because those points are going to be important. We will talk about that later. If I have that, okay, then I look, is this line optimized? No, then I optimize for that. Right? So first definition we define is the margin, right? And technically what we are trying to do, we are trying to maximize this distance, correct? What do we call that distance? Margin. So we are trying to maximize this margin. Find the best line that maximizes this margin from either side. So if we want to formulate this problem, we will write as, our goal is to maximize margin for W and B. That means you are solving to find the best W and B, because if you have W and B, you know the line. That's it, right? So you are trying to find the best line that gives you the maximum margin. So again, I look through different lines. For every line, I calculate the distance, and I find the closest data point to me, and then I store those closest data points. Then at the end, I look among all these lines, and I pick the line that had the largest distance from closest data point. Does that make sense? Finding a line that gives you the largest distance on the right to the closest data point and on the left to the closest data. If you have that line, you have a perfect separation. You have this street basically, you know, that there's no data point falling there, right? So we are maximizing for this. However, we need to remember something. This is subjected to. We need to define, here we have a constraint. Why we have a constraint? Because we are maximizing this, but this has a definition. So we need to say, remember that whatever you find here should be the minimum of this. We are maximizing for this, but remember, whatever you find for that should be equal to minimum among all the data points. Does that make sense? Because if we don't, remember what we discussed in the convex optimization? If you just solve for this, right, you ignore the constraints. The answer that you get doesn't guarantee to be the minimum. And the definition of margin should be minimum distance. So we add that as a constraint to guarantee whatever we solve is always the minimum among all data points.
Can you explain this graphically? What maximum and minimum?
So this is the definition of margin, right? Margin means minimum distance between a line and all points. So I have this line. I calculate all these distances, all of them. This is a for loop we write where you calculate all distances. Among those, I pick the one which is minimum. This one and this one, correct? From either side. It could be more than 2 points, actually. It just does like that. Now, I want to, so that's one line, correct? Next time, maybe my line is this, correct? So every time, for every line, I calculate that all those distances and pick the minimum distance to that line on the right and on the left, right? So that means now I have, for line L1, I have, let's say, 2 distances, 2 and 4. This is for class 1, this is class 1. For line 2, I have 3 and 3. For line 3, I have, I don't know, 4 and 6, and so on. Right? This is just an example of 2 data points on each side. And if I want to go among these lines, I need to pick the line that gives me the maximum margin, maximum distance. So this one gives me the maximum, correct? So, but when I'm looking at this line, when I pick this line, I need to be sure that this 4 and 6 that I pick are the minimum among all of them. If there is like a 2 and 3 in that class, then I made a mistake, right? The answer that I pick, this line, the margin for this line should be the minimum among all the distances in that line.
So I have just this quick question, like whenever we say margin, we are telling the distance between the a point and a line
Right.
of either class, right?
Correct.
So in an ideal case, like if you're pushing those lines to to reach the points, in an ideal case that should be 0, right? Like the margin should be 0. Like the line should touch the point on like either
No,
side,
no.
right?
How much you can push the line, that's
Subjective.
yeah. So we will talk about that. So
Okay.
right now, it's not like it's not basically forever. You can push this line to go forever, right?
So we just can't touch the point on either side. We just have to calculate the minimum distance from the point and the line.
Correct. So
Something like
for
that.
wherever this line, basically, so again, there's 2 lines on the center. These are conceptual, right? The line on the line on the corner. The line in the center is what we solve.
Yeah.
So everything you calculate with respect to the line in the center. So if for this line on the center, I calculate the margin to the right, margin to the left, right? So the point that stands here, there's this line, right? It's not like I can make the distance 0 because I actually want this distance to be maximum. I want this line to be the maximum.
No, I'm talking about the corner line, not center line. Like for the center line, we just want the distance to be maximum and equidistant, like maximum distance
Right.
from both of them. Like, but what about corner lines? The
So
margin.
let's answer your question. So imagine I send these 2 lines as far as possible. This is 0 now.
Yeah.
Correct? If that is 0, this is maximum,
Yes.
right?
Yeah.
But that's the same thing that we are talking here.
Yeah.
Right?
So that's what I'm asking. Like, so in an ideal case, the margin should be 0.
No. Again, margin is with respect to the line in the center, not the line on the corners.
Okay.
Corner, again, the corner lines is just a conceptual idea for you to understand why this works, right? The line in the center defines everything, is a decision boundary, right? Those 2 corner lines is just to tell you that our goal is to create a region, right? Like a street, basically, that no points should fall there. I want a clear region, right? And in order to achieve that, I basically find the right corner, left corner, and I find the decision boundary in the center of those 2, right? But our goal is always to find this. So the margin is this and this, right? By minimizing this, setting it to 0, you are maximizing this one, right?
So then what's the minimization in the constraints?
So minimization, think about it again, what does it tell you? I have 100,000 data points, right? When I find one line, these points are scattered around this line. Let's say we are saying that this is this perfect separation, no class overlap. Everything on the left, everything on the right, right, for both classes. So among all the points on my right, there is, let's say, it's example one data point that is the closest to me, right? That distance is margin, minimum distance among all data points, correct? So that's the definition of margin. My goal is to find a line that has the maximum distance on the right and on the left. So I always want to maximize the margin, but you need to be sure that whatever W and B you find, okay, that W and B, that margin for W and B that you're maximizing for, if you compare it against all data points, is the minimum among those. That means there should not be any other data points closer to you.
Sir, would you say that if we look at the constraint, right? Let's say if you don't have that constraint, then it will just maximize the boundary, and you may also have points on the street then.
No, what did I just say? No class overlap. At the beginning,
So that's what the constraint is.
so the constraint tells you that basically, if we have the constraints right now, basically tells us that for all these points, right, all the point on the left and on the point on the right, this margin that we define, let's say this here and this is here, this margins that we define, this and this, is the minimum distance among all of them. That's what it tells you. The margin that we found, which we found to be the maximum among different lines, okay, there is a margin. So there are two steps. You need to remember it this way. One is that you solve for lines. For different lines, one line at a time, you bring the line, you put it in the center, and you calculate all the distances. And then for the right side, you pick the minimum margin. And for the left side, you pick the minimum margin. Okay? Minimum distance, basically. That's which is the margin. Then you do that for all sort of lines. Then you pick among those lines the margin, which is the maximum distance. Okay? But you need to have this here because we define this. We have a definition that margin is the minimum of all of this. So that needs to be part of your constraint. It cannot be violated because you defined it. Okay? Does this make sense? Yes?
Yes.
All right. So our goal is to maximize this, subjected to that term, and this is for I from 1 to n for all data points. Now, let's try to simplify this equation. So rather than gamma of W and B, I'm just going to write gamma. So that stands for the same thing, okay? Subjected to, so this equation that we have, gamma equal minimum of this. If we try to rewrite it better to get rid of that minimum term, what would you do? I want to get rid of this term, minimum. What would you substitute? Gives you the same meaning. Think about what does it tell you? This is always equal to minimum of this for all data points. Right? What was that? Less than equal, right? Basically tells you that gamma WB, let's write it the other way around. W transpose xi plus b. 1, 2 is always greater than equal gamma, right? For all points. Right. Now, go back here. When this technically is the distance, correct? This equation here. The scale distance. So this is the distance, basically a scale distance, right? So, and we put that modular around it because we say that, we wanted this distance to always be positive, right? Now, we know that the modular has some problems with, the differentiabilities, right? Let's see if we can get rid of this modular. So when we are looking at this one, this is a point class, this and this. The distance here is basically W transpose xi plus b. And the distance here also basically is the same thing. Right. We know the distance for points on the class -1 are negative. Right, so if I remove this, that is a negative sign, correct? It's negative. And this one, as we remove that modular, is always positive. But we want the distance to be always positive. So how could we do that, make that positive for both of them without having a modular?
Square.
Square? No, not square.
Put a scalar value with the one expression on it.
But the one expression gives you 0 and 1. What else?
Subtract from the very positive value, something like that.
What's the class here?
+1.
What's the class here? What could you do? Multiply by their own class, right? So if you do yi times that, that your both always positive, right? And that's why we have -1 + 1 in this sphere, not 0, 1. Because we want to be able to do this. Okay. So we're going to rewrite this. So, next, I can just multiply that by cross multiplication subjected to yi W transpose xi plus b greater than equal. Yeah. So now yi W transpose xi plus b is the distance, the actual distance of basically that we have, right? Is greater than something. Now, norm 2 of W is a scalar, right? So gamma is a minimum distance, right? So if you multiply by a scalar, is a scale distance, correct? Scalar times minimum distance, a scale distance, right? So I'm going to here actually this here. I'm going to introduce a new variable called gamma hat and call it this basically. Rather than writing that, I'm just going to write gamma hat. Okay. Because also I don't want to have two variables, gamma hat and gamma. I'm going to write gamma in terms of gamma hat. So I get rid of gamma basically. So this means gamma equal gamma hat over Okay. So anywhere we have gamma, I'm going to put this term. And then also rather than that, I'm just have a gamma hat. Okay. So because it's just if you think about it, it's just gamma times some scalar. So it's just a scale version of gamma. So we are trying to maximize this subjected to yi w transpose xi plus b greater than or equal gamma. Does that make sense? All I did basically, I just introduced a variable, which I did it, we technically we don't need to do that. It's just, we will have so many variables. So just, rather than having gamma and w, just multiply them to get a scaled version of gamma. Okay. So, our goal is to maximize this and solve basically, keep that constraints in mind. What are the parameters, unknown parameters we have here in this problem?
W, B, and Y.
W,
So Y we know.
B,
And gamma.
right? So W, B, gamma are the unknowns here, something that we need to solve, right? Now, let's assume we have solved for this. Let's assume we have the optimal answer. So we call them W star, gamma star, B star. Okay, let's assume. We have that. Now, if we have these three as an optimal answer, if I bring some random or gamma, some random value of alpha, okay, I will bring some alpha, and I multiply alpha by this, all three. Okay, I bring basically like it's a 5 and multiply all three by 5 after solving them. Okay, so I have the optimal answer. I multiply all of them by a number, same number. Let's see what's the impact of that operation. So let's go back here. Rather than gamma hat, I'm going to write alpha gamma hat over alpha W2 star subjected to yi alpha W star transpose xi plus B star alpha. Correct? I just, wherever I had the original variables, I have a scale version of them, multiplied by the constants. Now, let's see what will happen here. Alpha as a norm 2, what happens to that alpha? As of modular, right? And this, because this like becomes positive value. So alpha and alpha, they cancel each other, so this becomes correct. Here also we have alpha, alpha, alpha. They cancel each other, all three, correct? So we have correct. So alphas they cancel out. Basically, that's what we are seeing here. But let's see what's the problem here, what I'm trying to show. I told you that we have the optimal answers. Then I also told you that, okay, for the same optimal answers, I'm going to multiply all of those with some constants. And that doesn't break anything. Everything works fine, right? So let's say this is a line that we learned, W transpose X plus B equals 0. Correct? We know this is W. Right? Let's say this is 2W. Correct? And so on. 3W. And so on. So every time I scale the W and B and gamma with the same ratio, the line, the direction of the line is the same, but W's is basically increasing, correct? That's not the same line anymore. What was the main promise that SVM had?
It will give an optimal line.
Only there is one unique answers. What's the problem here?
Like it
You have
can give-
unlimited unique answers. For any different alphas, you get a different answer basically, right? So that's a problem here. Every time for the same unique answer, if you same ratio, that is still a unique answer. And SVM tells you that no, there is only one unique answer. We're going to give you one unique answer. Okay. So what could we do to fix this problem? Now,
Could you just repeat that once more? Because ideally it does give you the same answer, because the alphas get cancelled out.
that's correct.
Yeah, so.
But alphas get cancelled in here. But your line is different. You have a different line, the 2W, 3Ws, right? When you replace it here, everything stays perfect. That's the problem, they cancel each other,
Yeah.
right? So it means that every time I scale the line, longer, shorter, with larger W, same line basically, it's still is going to give you the same answer. We don't want that to happen. We want it to be one answer. Now, which in-class problem we are? Okay, in-class problem. Right. So in order to avoid that, what we are doing technically, we fix the value of gamma with some constant. Let's say, for example, set gamma to be 1. Gamma had to be 1. Okay. Your in-class problem is that to prove why, if we fixate the value of gamma hat, this doesn't happen. So if gamma hat is fixed, a number, doesn't matter, 1, 0.5, 10, 100, this won't happen anymore.
Yeah, because that won't hold.
I leave that to you to prove. But that's the solution. So what we need to do is that we will prove, we won't prove, you guys will prove. We will force gamma hat to be a fixed number. And that fixed number, we will talk about it. Why, for example, 1, why 10, why 5. Right now, let's assume 1. It's like a default value. Also, lots of places we use 1. Okay. So let's see what does that mean for what we had here. So we had, our goal was to maximize gamma hat over norm 2 of W. So rather than gamma hat, I put 1, norm 2 of W subjected to yi W transpose xi plus b to be greater than equal 1 for I from 1 to n, correct? Anywhere we had gamma hat, we assigned 1. Now, this is the W transpose X plus B equals 0, the main line that we're solving. And this is on the left, this is on the right. So this is what was the definition of transpose xi plus b? Distance of the point, right? So distance of the point for any point is greater than 1. What does that tell you? That tells you by setting gamma hat is technically was the scale distance, right? When we set it to a fixed number, here 1, we are basically enforcing this region to be 1, 1. That means this was no distance, no points should fall within a distance of 1 to the left or 1 to the right. So all points should be at least 1 step away on the right, on the left. That's the definition of gamma hat here. So that means this is going to be W transpose X plus B equal 1. W transpose X plus B equal minus 1. So again, gamma hat was a scaled version of the distance, correct? it basically was gamma, which the minimum distance times the W, which known to of W. So a scaled version of the distance. So for that scaled version of the distance, we put a rule. We say that it should be 1. When we set that to be 1, that means no points should fall within 1 step to the right, 1 step to the left. Now, why 1? That depends on the data set. If I have a data set that has lots of separation, that means my points are far from each other. Maybe this gamma could be 10, you know, because the separation is really basically there's no overlapping, or I can basically have a really large margin. Or maybe I look at my data and it looks like this, really tight. Then I change the gamma corresponding to the gamma. Okay, so that all you need to do is to have it to be a fixed value. What value? It's your call. You look at your data, have some idea, and then choose the value of gamma. Does that make sense? Anyone wants me to go over it again? Which part from? This you mean? So I said we select gamma had to be 1, right? And I said that by default, lots of papers or basically out there, you see that we selected 1, but it doesn't necessarily need to be 1. It could be any other number, a fixed number. But how you decide, gamma hat tells you it's a distance, right? It tells you that no points should be on gamma hat a step on my right, gamma hat a step on my left, correct? So when I look at my data, let's say I have 2 dimensions, I visualize my data, and I see this distance, this region, let's say is 30, right? Or let's try some approximation, like I see, for example, I have 15 at least on the left, 15 on the right. So then I can pick a larger gamma hat, because I can enforce this region to be much larger. That means no data point should fall in 10 steps to the right, 10 steps to the left. But if my data is really dense, the data set that I have, then maybe gamma hat should be 0.5, for example, right? A much smaller value. It's just you select a fixed number again, based on how your data looks. Question? No? So is this clear for everyone here, what we're doing? All right. So, yes.
How do we look at the data in the slide?
Visualize it.
Visualize.
Visualizing it. So first thing you need to do is that, remember, this is a linear SVM. That means your data should be linearly separable. Okay, that means you should be able to fit a linear line to separate this data. Okay, so that's step 1. If you're able to do that, that means I look at the data, I can see that I can draw a line, separate this from each other. If your data set is in a larger dimension, we cannot visualize it in a larger dimension, but you can do some linear tests, right? But if you want to visualize it, you can do maybe a 2D, 3D pairs of different dimensions, and you get some idea. Okay, I see this. I can do linear line here. But when I visualize my data, if I see both classes are far from each other, that indicates that I can have a larger gamma. If I see the classes are really close to each other, then going to have a smaller gamma. Just some visualization, right? So now let's look at here. We are trying to maximize this, considering this. Find maximize for W and B. Find the optimal W and B that maximize this. And remember that whatever you get, this should be always greater than 1. Correct? So if I'm trying to solve maximize 1 over W, and that's maximization, do you agree? In order to maximize that, I should minimize W?
Yes. Yeah.
Right? So I can write this as minimization of 22. Also, we add 1/2 behind it. To cancel later the 2 to the power of 2, right? So. Now. So we are trying to minimize this with respect to W and keep this in mind. Actually, let's write here. So this term, this equation here, this definition called vanilla SVM. Vanilla SVM. Anytime you hear the term vanilla for a given algorithm means the base algorithm for that, like vanilla justification, vanilla neural net for vanilla SVM, right? So this is the original version, and other derivations of SVM comes from here always. Okay, so that's the starting point for different branches that we're going to basically learn. So we are going to start with hard margin SVM. Okay. Now, this is the first type of SVM that we're going to learn. Again, is linear SVM. Okay. Hard margin SVM. The main characteristics of hard margin SVM is that the term hard, it does not allow for misclassification. It does not allow for any points to fall within that street. All points should fall on the correct side, basically. Right. So no class overlap allowed. Okay. So hard margin SVM is only applicable when you're looking at your data is perfectly separable. If you have class overlap, this is not the approach. Okay, we will see the next one later. Now, so let's look at here. So we are trying to minimize that subjected to this. What do you see here? If you look at the objective function, what could you tell me about it? What else could you tell me about the function? It's convex, right? It's a norm to a convex function, norm to a square also. When you're looking at the constraints, what could you tell me?
Also convex.
It's a convex set, right? We proved, I remember I wrote 5 types of convex sets, basically. So it's a convex set. But when we went over the convex sets, we said there are two sets of constraints: equality, inequalities. Both of them for equality should be equal to 0. For inequality should be less than equal to 0. But this is greater than equal to 1. So we need to convert it to less than equal to 0. So we rewrite this as 1 minus yi w transpose xi plus b less than equal 0. And this is a convex set. Correct? So we are trying to solve this. We are trying to minimize this. And this is the constraints that we have. Let's answer this. How many parameters you have here? Parameters means the unknowns that you are learning. So how many you have?
N. 2n.
That's 2. Because those are vectors, they are not matrices.
So those are vectors.
Yeah.
So how many unknowns do you have?
2.
How many unknowns do you have inside W?
We have 2 unknown vectors.
W, what does it carry? 1
Per x.
per column.
Yeah, per column.
So how many columns do you have? D.
D.
How many W's you learn?
D.
D. How many unknowns you learn? D plus 1. Number of parameters you learn, D, 1 W per column, and 1 bias.
Yeah.
D plus 1 is not 2. That if it's, the reason I want you to be sure that you count this correctly, because the complexity of 2 versus D plus 1 are much different, right? So, how many sets of constraints you have? How many constraints you see there?
And
Right. So you have n. So we have a problem which has D plus 1 parameters and n constraints. Okay. So this could be an easy problem if D is small, right? You know, if D was small, then you could just solve it using a normal convex problem. But majority of the time, most of the time, D is not small. So D is large. So the dimensions that you have are large, right? And that's where we're going to try to solve it using Lagrangian. Okay, which we saw that in the convex optimization, convex function plus convex sets, we're basically doing Lagrangian. And what was the main goal of Lagrangian? We bring the constraints added to the objective function with the goal of forcing the constraints to go to zero. If we do that, we basically remain with the objective function, and then we just take a derivation for objective function. So we rewrite this as Lagrangian over first always the original parameters W and B. Then rewrite the original objective function, which is 1/2 W2, right? Because it was a minimization, you add something to it plus. What do we add? We bring the not the less than equal part. We bring the constraints up multiplied by something called Lagrange multiplier and sum across all n of those, right? We have n constraints. We multiply each constraint by alpha, right? So plus summation of for I from 1 to n, alpha I times 1 minus yi, W transpose xi plus b. In case you are wondering why alpha not beta, that's just a random name. It's just, it doesn't matter. A, B, C, you know. That means here we will have this. This one is also vector. So we are learning for the vector W, which is D parameters, B, which is 1 parameters, alpha is n parameters, right? So these are the unknowns that we are basically solving for. Now, we know, we basically discussed that when we are solving for Lagrangian, we are trying to minimize for the original variables. And then at the same time, we are trying to maximize for alphas, right? And remember in the previous class, I also mentioned that if we have convex function, convex sets, we can solve this the other way around also. Max mean. Right? You can either first solve for that and then this, or solve for this and then that. And the way that it technically works is that doesn't matter whichever you solve for. After you solving, for example, for W and B, this is what we wanted. If we solve for W and B, we find the optimal answer. We replace that optimal answer back into L. Then we have done with W and B because we solved for them. Then we solve for alpha. If we solve for alpha, we replace alpha back and then solve for W and B. But we want to understand then why it might be beneficial to, or it is beneficial to do max mean rather than min max. We're going to discuss that now. So we want to do max mean. Now let's look at here. So we have convex plus convex, right? The convex, right? So we want to minimize with respect to W and B. What would you do? Convex function, you want to minimize with respect to W and B. Take a differentiate, right? Or basically take that, take a derivation with respect to W, and take a derivation with respect to B. Set it to zero, right? Because convex plus convex, where do we have, right? So let's just start with W. Solving it for W is equal to 0. So here we have two W's and 1/2. They cancel each other, so it comes out W. Here we have, if we take a derivation with respect to W, we have summation alpha I, yi, xi, right? And there's a negative minus summation alpha I, yi, xi equal to 0. So that means optimal value for W equal alpha I, yi, xi. Is that okay? So now let's take a derivation of that with respect to B. So we only have here a B, which is alpha I times yi times B. So it comes out summation of alpha I, yi, right? Right? So when we took a derivation with respect to W, we got the value for W, but for B, we just reached to something, but we didn't find the value for B. Okay. So, because we already solved for W and B, the minimization part, all you need to do is that pick whatever you found, replace it into the Lagrangian function, and then solve for the next unknown parameters. So we are trying to solve the maximization with respect to alpha. We dropped the minimization because we solved for that over Lagrangian, and we replace W with W star, B star, alpha. That means we have solved for those two. So all we need to do is that any place that we have W, we replace it with this term. Okay. So let's quickly rewrite that. So that is equal to W transpose W plus summation of I could just expand that summation of alpha I minus summation of alpha I, yi transpose xi and minus summation of alpha I, yi, correct? That's the expansion of the Lagrangian term. Now, anywhere I have W, I'm going to replace it with this term. So in order to, because this is over I, I can just read it with I from 1 to an alpha I, xi transpose, because the W has a transpose. So when you are looking, if you apply transpose to this term, because W had a transpose, right? Alpha and Y, they're scalar. Transpose doesn't do anything. X is the only vector here, because these are I, X is a vector. So X is the only one that gets the transpose sign. So it becomes alpha I, yi, xi transpose. Times, there was another xi here. Right? So then we have minus alpha I, yi. So one thing I could do to avoid the confusion and indices here is rather than I, for this one I write J. Is that okay? Yep. Just in order to don't confuse this I indices here. They're the same thing because they go over the same number. So you just rather than I, we just write G. Okay. One thing here. A1 plus A2 transpose time A1 plus A2. Right? We know that this is, for example, is A1 transpose A1 plus A1 transpose A2 plus A2 transpose A1 plus A2 transpose A2, correct? Also, we know we can write this as, if we are looking at the indices, do you agree I can write this as I from 1 to 2, J from 1 to 2, AI transpose AJ? Do you agree with this? Yes? So, do you agree this is the same thing over there? This transpose itself. A1 plus A2 transpose itself, right? So this multiplication becomes 1 over 2, I from 1 to n, j from 1 to n, alpha I, alpha j, yi, yj, xi transpose xj. Again, look at here. We have A1, A times transpose itself, right? So what we reach to is two summations repeating over itself twice, AI transpose AJ. So here, apply the transpose to this term, becomes alpha I, yi, xi transpose, times itself, alpha I, yi, xi, but change the I indices to j. Alpha I, alpha j, because the alpha scalar, so I can swap the order. Alpha I, alpha j, yi, yj, xi transpose xj over two summations. Right? So then we have plus alpha I. Here, this is the same thing again. Alpha I, yi, xi times alpha j, yi, xj transpose. This xi is part of this, right? So this gives you, it has a negative minus alpha I, alpha j, yi, yj, xi transpose xj. Doesn't matter, xi, xj, xj, xi, they're the same variable, right? They're the same data. Minus. Now, what could you tell me about this? Alpha I, yi times b. What did we learn here?
0.
Alpha I, yi summation is 0. Times b is always 0, right? So this is 0. Now, when you are looking at this and this is plus 1 over 2, that's plus minus 1. So they can subtract from each other. It becomes minus 1 over 2, right? So continue here. Basically, we are trying to maximize for this. Minus 1 over 2, summation, alpha I, alpha j, yi, yj, xi transpose xj plus summation of alpha i's, I from 1 to n. That's basically what we reached to, right? Now, we picked this, we replaced what we found here, and we reached to that term. Okay. However, you need to remember two things. One is that whatever we are solving here, it still has some constraints. What are the constraints? First constraint is this. This should be zero, whatever we find. Because if this wasn't zero, we couldn't get rid of also this, right? So you need to be sure whatever you get has the value of alpha I, yi equal to zero. Because if you don't write this and then you get an alpha which that violates that, then you have problem here, right? Because that was the assumption that you have. That term is equal to zero. The other thing is that alpha I. What do we know about alpha I? What was alpha I?
Lagrange multiplier.
Correct. For what type of constraints?
H of x, right?
What type of constraints is?
Inequality.
Inequality. Inequality constraints. What was the sign of Lagrange multiplier? Greater, should be greater than zero. You cannot pick less than zero. So you need to force this to be greater than zero. Okay. Now, well, this one doesn't have summation over because this is a summation. So whatever we solve, whatever we are solving here for alpha, which we are maximizing that term with respect to alpha, we need to remember two things. Whatever alpha we find should be always positive. And across all data points, this summation of alpha I times class is either -1 and 1, should be zero. This balance should be balanced, right? So now someone tells me, how many parameters do you have here? How many unknowns do you have here? How many of those do you have? N. How many constraints do you have?
N.
Which one is N?
Why?
N. How about that then? That's not a constraint. N plus 1. This is one operation, right? So you have N plus 1. Now, let's do a comparison side by side. The original objective function, how many parameters it has? P plus 1 and constraints. By swapping the order of min max to max mean, the function that we derived at, we reached it. How many parameters it has? N. Is no longer dependent on columns. What does it depend on? What is N?
Number of segments.
Number of data points you have, correct. The more data points you have, the more parameters you learn. What type of algorithm is this? Non-parametric, right? Parametric, it depends on D. Non-parametric, it depends on the data that you have, right? So the larger the data set, the more parameters you basically learn. Now, that also tells you one thing. SVM is not a good classifier or a good algorithm for large data set. If you have in billion records, no, don't even try it, okay? For your project, if you want to do SVM, sample from your data set because the more data you have, the longer the wait. You know, we have had the students that they wait like 3 days and they came back like, I have been waiting for 3 days, my code is still running. And sample from the data if you want to do a SVM in your project, do a smaller size. Now, okay, so we are trying to maximize this for alphas and solve this. Now, let's also understand one thing, this concept of min max and max mean. what does it do actually in the back end, you know? If you think about it, because we first solved for W and B, we got rid of W and B, but we haven't found the W and B, right? We just found a formula for W, right? Not the value for W. We will find the actual value for W after we found alpha. So W is a function of alpha. That's why we no longer depend on D. If we solve it the other way around, you find alpha, and then alpha becomes a function of W, basically. Right? You see this how you're solving it, but then D, because W was was dependent on D, it becomes more expensive. Right? So whenever you find alpha, you need to replace it and to get W. But for B, this is your next in-class problem. You need to prove B is 1/2 over So basically, this tells you that if you have these points, class +1, class -1. First, this one expression over class 1, this ones. Find the minimum distance. This is the minimum, right? This one minus the maximum is, because this is negative, so this is the maximum one among the other class, right? And this one, this gap divided by 2, that becomes the intercept. And you want to prove that basically. Okay. So
So,
yes.
just to understand, is that basically the dual of this?
This one is the dual of that.
Yeah.
Correct. So yeah, so that's a good point. So this what we basically write here, this L form that we have, that one is the dual form. This is the original form, that's the dual form. Right, so that's correct. Okay. So we can continue for now. Now, when we are looking at this problem, first thing we see, so this is no longer linear programming, this is quadratic programming. Okay, so it's going to be a bit different when we want to solve. Now, let's assume we have solved for alphas. We will talk about how later, but now let's assume we have let's see all this alpha stuff. We have solved for it. It's either a vector or you have it as a sparse matrix, for example. Right. Now, when we talked about the convex optimization, the Lagrangian, after solving, what did you need to do?
Test it out.
How do you test it?
You plug it back.
No, but there was some other approach. There were some conditions.
Yeah, the effects.
KKT conditions, right?
Yeah.
So you need to verify these conditions in order to understand that if the answers that you have is correct. Now, when we go over the KKT condition, first one was a stationarity, right? which basically tells you that if you take a derivation of the original objective function, Lagrangian with respect to W and B, you should be able to take derivation and set it to 0. It has a station point, right? So it means derivation of this with respect to W, solving for W, should be 0. Derivation of this with respect to B, solving for B, should be 0. Which we proved that, right? We took a derivation with respect to W and B, and we were able to set it to 0. So that is proven. 2 was primal feasibility. What was primal feasibility tells you that if you take a derivation of Lagrangian with respect to Lagrange multipliers, if its equality should be equal to 0, if its inequality should be less than equal to 0. So here we had inequality constraints, right? So that means the derivation of L with respect to alpha I should be less than equal to 0. When we take a derivation of L with respect to alpha I, what did we get? Where is it? No, we get GJX, right? Right? Yeah. So, or basically, this is the GJX, you know, this term is GJX, right? The inequality constraints. That's why we brought it up. What was the sign of inequality constraints? Was no, here. Negative. So this derivation is negative, which is again 1 minus yi W transpose xi plus b, which is less than or equal to 0. So this is also proven, right? We already had this. Third one was dual feasibility. And dual feasibility tells you that the alpha I, which is the Lagrange multiplier for inequality constraint, should be positive. Should be positive. That's enforced, right? Which is correct. We enforce that, right? So whatever we basically force that to be alpha. Now we assuming here we have solved this, right? We haven't solved it, but assumption here is that let's assume we found these alphas. Now let's go to a fourth one. What was the fourth one? Complementary slackness, right? So fourth one. What was the definition of complementary slackness?
You multiply the Lagrange multiplier with the constraint, it should give 0.
Lagrange multiplier times constraint, doesn't matter, equality or inequality should be 0. Because that was the goal, to bring it up, force it to go to 0. So alpha I times the constraint, which was 1 minus yi W transpose xi plus b, should be 0. But that's the part. We don't know if it's 0 or not yet, right? So we know two things. We know alpha is greater than or equal to 0. We know the constraint is less than or equal to 0, right? So let's say scenario A. What if alpha that we found is positive? Is positive, because it should be positive, greater than or equal to 0, right? If it's alpha is positive, what could you say about this?
0.
Should be 0, right? 1 minus yi W transpose xi plus b should be 0. That means yi W transpose xi plus b equal to 1. All right. So, scenario B. What if 1 minus yi w transpose xi plus b is less than 0? Then what happens to alpha? Okay. So this means also yi w transpose xi plus b is greater than 1. If this is less than 1, this less than 0, that means this is greater than 1. Right? Okay, so we have learned two things here. Let's try to map those learning on this board that we have. Let's start with this one. Alpha I, this optimal alpha, is greater than 0. yi w transpose xi plus b equal 1. What was this term? yi times w transpose xi plus b. That was the distance, right? For either class. If it's equal to 1, which point is referring to?
Yeah.
Which ones?
Yeah, gamma.
The x's? No, think about it again. The distance, positive values, doesn't matter which class, equal to 1.
All the ones on the border, basically.
All the lines that are, all the points that are on the line, one step exactly to the left, one step to the right, because it's exactly equal to the distance exactly equal to 1. What's this equation? W transpose x plus b equal 1 equal minus 1. So this point, let's say this point, not that. Right? Those 3 points, this is what it's referring to. So what do we know about those 3 points? Alpha I star greater than 0. Alpha I star greater than 0. Correct? Does that make sense?
Yes.
So this one now, alpha I is 0. Distance greater than 1. Positive side of the distance greater than 1. Which points it refers to?
The interior points.
All other points, right? This and this. Is that correct? So now let's understand what we are seeing here. Among all the data points that we have, right? Some limited number of data points will get alpha greater than 0. Every other data points that are in the correct side of the line, they get an alpha equal to 0. Let's see what's the impact of that. What's the B? So alpha if it is equal 0 or greater than 0, right? When you want to calculate W, alpha I, yi, xi, for all data points, correct? For majority of the data points, alpha is
0.
0. What does that tell you about those data points?
They're interior.
They don't have any impact on the W, correct?
Yeah.
So those data points, they don't find W. Even for B, they don't find B either. Right? And that's why when you hear the term support vector machines, these data points are called support vectors. The rest of them are garbage. That's the reality of it. Your goal is to find these points that you're supporting this boundary. As soon as you found those, you have W and you have B, and you can get rid of the rest of the data points that you have, because they don't do anything in reality. Does that make sense? So you find this now. and you have your W's. Then you find your B basically. Now let's say we, for example, have X test, and then you want to find Y test, one data points as test stage, right? So you can say Y test equal. So all you need to do is simply see which, because this is discriminative classification, right? Which side of the line the point will fall, right? So you calculate the distance, which is, you just basically simply replace the point there. So it's going to be W transpose X test plus B, W star, right? We calculate that. That's either positive or negative, right? So if it's we use a function called sine. In Python, for example, it's like if it's positive, it returns you +1. If it's negative, it returns you -1. So that's how you make prediction. Sine of this value, if it's positive, gives you +1, negative gives you negative. Now, this technically means that to calculate this, sine over, pick this over the support vector points. So rather than I from 1 to n, for I points that belongs to support vectors, only those 3 technically, you sum over only those 3 times alpha I, yi, xi transpose x test plus e. So this is technically what you need to calculate at testing this step. Multiplication of alpha, y, x of support vector transpose x test plus b, and the sign of that, right? In reality, we don't need to do that because we can store w. So rather than keep repeating the same thing, we can store w as a value and just do multiplication w transpose xi. Yes.
So when we say xi and yi in that formula, do we only take the support vectors? Or
Yeah,
do we take...
I belongs to support vector points.
Okay.
Only those 3 data points. We only look through the rest because the rest of them alpha is 0. There is no benefit of that multiplication.
The transpose is on alpha and y as well, right?
Alpha and y are a scalar. X is a vector. X is the only vector here. That's why every time I carried on the transpose, I didn't apply it on alpha and y because those are just a number. Any other question? Do you think it's clear? Yeah. All right, let's take 5 minutes. Okay, let's continue here. So. Our goal was to maximize this for alphas, right? So that's the only thing that left. If we find alphas, we know W, we find W, we find B. And here, I basically wrote, let's assume we have alphas, right? But we don't have alpha, and we want to talk about actually how we are going to solve for alphas. Now, coordinate descent or ascent. There is an algorithm, basically an optimization technique. We're going to talk about coordinate descent or ascent. Depending on if it's maximization or minimization, the descent or ascent will change. Now, here, for example, we are trying to maximize J with respect to all these alphas, or you try to minimize J with respect to all these alphas, right? So when you have series of unknowns, like alphas, there are still two ways that, like, for example, we can solve this. One is that we can just simply using something like a gradient descent, or just basically take a deviation and solve it for alphas, right? So that's one approach that we could take here. Do something like gradient. There is a problem with that. The problem is that when you have multiple unknowns, it's hard to solve for all of them at the same time, right? Because every time that you solve for n alphas, not one alpha at a time, right? So it becomes much more challenging. Now, when you go into a technique like called coordinate ascent or descent, basically the idea is that when you have this maximization or minimization again, and with series of unknown parameters, the idea behind it is that you try to solve them iteratively, one at the time. Okay, how? Similar to a gradient descent at the beginning, what you're going to do is that you randomly initialize alphas. At the beginning, randomly assume alphas, for all the n alphas that you have, right? Now, so this is coordinate ascent or this. Then, what we can do is that, so in step 2, I have now a vector of alphas randomly initialized, right? In step 2, what you do, fixed all alphas, n minus one of those, except for one, basically. Among all n alpha, keep one of them out and keep the rest of them fixed, you know? So n minus one alpha is going to be fixed value, whatever we initialize. So 2.1, we fixed n minus one of alphas and solve for that remaining I, alpha. How do we solve for this? There are different ways that we can solve. One is that I already know I'm trying to solve this problem, maximizing this, right? If I have all the alphas except one of them, I can find that one alpha, an alpha that maximizes this, one alpha, correct? Another way is I can focus on this. Alpha I yi equal to 0, summation, right? I have all alphas, one is missing. That means that alpha becomes minus summation of alpha j yj when j is not equal to I divided by yi. Correct? Because again, alpha I yi equals 0. It's like, for example, if we say alpha 1 y1 plus alpha 2 y2 plus all the way alpha n yn equal to 0, right? I have all these alphas except this one. I want to find that. So that becomes this summation divided by this as negative because it goes to the other side, right? So I will find this alpha I. Now in the next iteration, I replace that whatever I found back into the vector. Now I go with the second alpha and I solve for the second alpha. Fix everything, find the second one, replace it. Go solve for the third one, solve for the fourth one. And we repeat this in a loop until convergence. Constantly, basically, keep n minus one fixed, solve for one, replace it back. Keep another n minus one fixed, solve for another one, replace it back, and so on. Does that make sense? So 2.2, replace, let's start here, alpha I star in alpha, and solve for next alpha I. I'll repeat this, repeat until convergence. Basically, you repeat this at some point, it will finally basically reach to the point that doesn't matter how much you change, this doesn't change anymore, right? Now, this one is still a bit challenging because it's a lengthy process. If you think about it, it's not that you go over them one time. You have n data points, and probably you're going to over each of them series of times. Right? Every time you change one, it has impact on the other ones also, right? So this takes a long time, right? Now, one of the alternatives, algorithms that we can use, I think it's going to be your homework. So, sequential minimum optimization. And it is minimal or minimal optimization. Let me see, SMO. Sequential minimal optimization or sequential minimal optimization, something like that. Minimal. Sequential minimal optimization or SMO. So you will receive after this class, you will receive a paper. It's like three or four page, which is your homework. So you need to read the paper and then answer the question that basically the homework gives you. But sequential minimal optimization is the idea is the same as this coordinate ascent. The difference here is that rather than to solve for one at a time, you solve for two at a time. Fix n minus two and solve for two, right? So this the whole idea is that we try to optimize it somehow to so we don't need to iterate that many times, right? So this is going to be your homework, okay? See, on this. No. So because just emphasize, this is a minimization, right? The problem that objective function that we have for alpha is maximization, right? So all you need to do is multiply it by negative. So that means we are going to, rather than solving for maximization, we solve for minimization over 1/2. So we basically solve for minimization. And all we need, we multiply the objective function by negative. Okay. So what we saw here was hard margin SVM. A classifier technique that it tells you that no class overlap shall exist. That means if you're looking at this data set, no points from either class should fall within that boundary or on the wrong side of the line, basically. It should be a perfect separation. But next thing we are going to talk about, it's called soft margin SVM. Okay, this is the second type of SVM that we are going to learn. And the idea of soft margin SVM is that the points could fall on the wrong side of the line or even within the margin. Okay, so if you have a data set that looks like this, you cannot do hard margin SVM. You need to go for soft margin SVM. So that's the first step for your project. If you want to do SVM, do visualization. If you see class overlaps, soft margin SVM. Okay, so soft margin SVM again is linear. It's important. Remember again here we will talk about how to make it non-linear later, but at the moment this is a linear classifier, right? Where class linear and then as class overlaps are allowed. Okay, so now we want to formulate this problem. We just have an idea. We want to have a version of SVM that allows for class overlap. So we need to formulate. In order to formulate this, we need to start from beginning. Where is the beginning? Vanilla SVM. That is the base. You pick that, you create from that. So we picked vanilla SVM, we created hard margin SVM, right? Now we will pick vanilla SVM, we create soft margin SVM. So first let's start. Let's rewrite what was the vanilla SVM. Vanilla SVM was, we want to minimize this term subjected to 1 minus yi w, oh no, it was yi w transpose xi plus b greater than equal to 1. All right. So This is the definition, the original definition, right? Now, what we are saying here, we are saying that all points should
Be on one side.
be at least one step away. The distance for all points, doesn't matter, positive or negative, this side or this side. And the line should be at least one. That was the definition of vanilla SVM, right? But now what we are saying, we want to say for some points, they should be able to fall on the wrong side of the line, right? So we want to relax that definition. Not all points should fall one step ahead, right? Some points are allowed to fall within the margin, that means less than one step, or on the wrong side of the margin, correct? So if you want to tweak this problem to account for that definition, which part do you think you should tweak?
Right-hand side.
The
RHS.
the constraints, right?
Yeah.
This part you want to touch, right? So this is right now we say it should be greater than one. What we are going to do is simply add something called sigma I. Okay. So we introduce another unknown variable. We let the model to decide. Okay. So we want this to be greater than one, but we know class overlap will happen and that might keep the model in a long loop. So we allow the model, hey, this term actually is called the slack variable. Okay. We basically told the model, hey, for some of this point, you are allowed to pick some number, some scalar. This is a scalar, right? So let's look at here. This point on the line, this point, this point, this point. These are on the correct side of the margin, correct? Do they need any slack?
No.
So
Yes.
same here. We don't need a slack. Now, let's look at this, these points. This is the decision boundary. Let's start with this point. Which side of the boundary is that point? Positive side still, but in the margin, correct? What do you think the slack should be for that?
A small slack, like
0.5
But it's like what range?
between 0.5 and 1.
Between 0 and 1,
0.
right? So because if it's more than 1,
we're on the other side.
is this one.
Yeah.
So this point, this point and this point, basically, they get a slack less than 1 between 0 and 1, correct? Now for this point, and this point, and this point, any point that have been totally misclassified, right? The slack should be greater than 1. That's how we could allow for this term to happen, correct? We don't know those. The model needs to learn those variables, right? We say that based on the definition of a slack, that's how it should be. If it's in the correct side, there shouldn't be any slack. If it's in the wrong side, should be a larger slack. If it's within the margin and the correct side, a slack between 0 and 1. Does that make sense? Because if you look what will happen, for these points that are correctly classified, if they are greater than 1, so a slack is 0. For this point fell before the within the margin, but on the right side of the line, which is positive still. So whatever we get, the distance should be positive. So 1 minus something less than 1, right? But if it falls this side, that is a negative, correct? So this should be greater than 1. 1 minus something larger than itself, because it's a negative, it's a wrong side of the line. Does that make sense?
Yes.
So now, so we introduce a slack, and we basically say that, okay, you know, for some of these points, wherever you deem it's appropriate, just give them a slack, right? And anyone tell me that, what do you think could be the potential problem here? So we are telling to the model, wherever you find it's appropriate, basically, wherever you want, basically, cut a slack over there, right? Don't be harsh on those points. What do you think will happen?
Sometimes the slack could take a negative range and it could push even the point on the right side to the wrong side.
Now, let's say a slack is something positive. Let's say a slack is up. So I said it's 0, 0, 1 greater than 1. So a slack is always positive. Think about just think it from the perspective of a model. Imagine you are a model, right? Model as a computer model, okay? Algorithm model here. So, and I give you a problem, and I tell you that to separate these classes from each other. And I tell you that whenever you feel comfortable, you know, you can just cut some slack, and so your error doesn't go up.
I'll try to take the least number of slacks.
What was that?
It might cut the entire thing,
Cut the entire thing.
not entire, but once.
So if I have this, let's say. If I tell to the model, hey, give me the best answer, wherever you find important, like possible, just cut some slack. The model will put everything on one side of the line and cut the slacks for all of them.
Yeah.
Correct? You say wherever you find important or necessary, just find a slack variable. So model will overfit it this way, just put everything basically on one side, right? And then that the problem is solved. So what does that mean? That means we need to penalize the model on number of slack that it gives. It shouldn't be allowed to slack for all data points, only when it's necessary. Similar to regularization, we are going to regularize the slack parameters, basically, the slack variables, right? So we were trying to minimize this subjected to solve with WMD, subjected to, we introduce a slack. So what we are going to do is that, because it's a minimization, we are going to add something to it. It's going to be C over summation of slacks. Similar to regularization, lambda times a norm over the thetas, right? Here we do just summation over slacks. The slacks are basically some positive value. You sum those positive values multiplied by C. C is a constant that you decide, right? If this is too large, this goes up, right? It's minimization. You see, so the model needs to find a balance. If I want to minimize this, I cannot give too much of this. Because if I give too much of this, the total minimization goes up, right? So again, same thing as regularization. We try to find the balance between this and this. So, does this make sense for everyone? All right. Now, what we can do is that basically we can, we have this minimization. We can rewrite, we know this is convex, this is positive also, convex. We know this is a convex set, so we can write this as inequality, right? So, this becomes 1 minus sigma y minus
not just not a support vector and add a flag.
Yes.
Why don't we just add a new constraint instead of like having the penalty? Like if it's not basically a support vector, if it's less than the support vector of a particular class, we just have a new constraint for it where it can have a slack.
That's a great point. So what would you define? Let's just make one example. What would you define as a constraint?
So let's say basically we know that yi w transpose xi minus b, if it's equal to 1, it's a support vector. So let's say if I is equal to -1 class and it's less than 1, then it falls in the straight. So you give it a slack. And if I is equal to 1 and it's greater than 1, then it's again on the straight. So you give it a slack. So you don't even need a penalty on top.
So let's poke a hole in that theory. So first thing you say that look at the complexity. You're actually defining, hard coding the definitions of the slack for each scenarios that could happen. Correct?
Correct.
The next thing is that you are not learning sigma I. Sigma is not it's just your constraints.
It's just penalty.
Here, sigma is part of your objective function. You need to basically learn it. Over there, you need to decide on the sigmas, right? What you are saying.
Yeah, correct. We'll have to give the sigmas.
Correct. So is basically your call on what sigmas is
Yeah.
we need. So here we allow the model, find the sigma where is appropriate, but think also if you pick too many sigmas, the cost is high, right? So we have convex function, we have convex set. We know the drill. So remember, I said similar to maximum likely distribution, you're going to repeat the same thing over and over again for a couple of chapters. So we write this as Lagrangian. We solve for WB sigma. Let's write this. We have one inequality constraints. Actually, no, we're missing. I'm missing one constraint. Sigma should be positive.
Yeah.
So that's another constraint. So whatever sigma the model picks should be positive. Okay. So sigma I should be less than equal to. So we have an alpha for first set of constraints. Then we have a second set of constraints. We're going to define a beta. Okay. We have W, E sigma. So we rewrite the original objective function. We bring this one up, so it becomes plus summation. Then we have this one comes up.
Why is there a sign change in
Which one?
the sigmas? Sigma I and then.
Sigma where
Oh, so here it's basically positive and here it's negative.
here is positive.
Yeah, and in the second scenario, it will become negative.
Inequality constraint should be always less than equal. So I changed it. If you want to do convex optimization, remember I told you always inequality constraint, you need to convert it to less than equal. So it becomes basically negative of this actually.
Yeah.
Negative of this is less than equal. That's correct. Anytime again, convex optimization, it should be less than equal or equal to 0. So this becomes minus beta j sigma j. We also keep this I rather than j, but it doesn't matter if I want. Right. All right, so before we before we solve this as Lagrangian, let's go over this. Tell me how many parameters do you see here in the original form, this one?
W sigma.
Give me numbers. Count them out. How many you have of each? How many W's do you have? Okay. What else do you have?
Sigma, so D sigma.
N sigma.
And so,
What else do you have? B. Right? D plus N plus 1. How many constraints do you have?
2n.
2N. N here, N here. With 2N. What was that?
We don't have +1 for each.
Why plus-
Before we had n plus 1, right? Now we have 2 constraints, it's gonna be 2n plus.
No. So constraints is, this is one constraint, one set, N time repeats. This is repeats N time, 2N constraints. The other example that we had was summation of sigma alpha I y I equals 0. That was one constraint, because it was summation among all of them. This is individual constraints, right? So that was, if it's summation, this covers one constraint, here is individual. So, okay, so we know that we are trying to do min max over L. Original variables are W, B, sigma, and we are solving for alpha and beta. Actually, I need to add something here. So alpha and beta, they are both inequality constraints Lagrange multiplier. So both of them should be positive. So alpha should be positive. Beta, alpha I, beta B should be positive. So we know in order to solve this, we could also solve the other way around. Maximization, minimization. So we know this is basically convex plus convex plus convex, just that's a convex, right? So when you try to do minimization for W and B and sigma, what you need to do, take a derivation, set it to 0. So take a derivation of L with respect to W, solve it for W, set it to 0. Let's see what do we get here. It's there. We have a W. We have
W transpose.
summation of alpha I,
yi,
yi, xi,
actually.
right? So it becomes W minus summation of alpha I, xi equal to 0. So solve for B. We have one B here, so alpha I, yi, B becomes basically minus alpha I, yi minus summation of alpha I, yi equals 0. And next one, we take a derivation with respect to sigma I. If you take a derivation with respect to sigma I, let's see what we get.
C.
We get C. Here also we have sigma I.
Minus
Alpha I times sigma I
minus alpha.
minus alpha I
And beta G.
And
minus
summation of-
BWG. Because you take derivation with respect to one of them, just so you get C minus sigma I, alpha I minus beta J equal to 0.
C is alpha plus beta.
Okay. So with for the first part of the problem, which was the minimization, we took derivation with respect to original parameters, set them to 0, and when we reach this tree, what was the next step?
Put that back and
Right. So replace what you have back into the Lagrangian, rewrite the equation, and then solve for the rest of the unknown parameters that you have. So I'm going to, before adding those, I'm going to expand this so it's easier to follow what's happening. So we are trying to maximize L for alpha and beta. Where we have optimal W, optimal D, optimal sigma. And we solve for alpha and beta. So this is 1/2 W transpose W. We have plus C summation of sigma I. Let's expand this one. We have an alpha I, summation of alpha I. Then we have summation of minus summation of alpha I, sigma I. Then we have alpha I, yi, W transpose xi. Plus minus summation of. Then we have summation of alpha I, yi, b. Minus summation of beta j sigma j. I just expand this as much as possible, okay? Now,
Consider that, right?
now we will bring W, that's because W is the only one we can substitute. And we will substitute it back here, where we have a W, we see, okay? So, you remember for this one, we already did the substitute in the previous step, right? I know it becomes 1/2 summation alpha I, alpha j, right? So 1/2. Alpha I, alpha j, yj, xi transpose xj. I'm going to leave these 3 out for now. This one, we know exactly also gives the same thing as minus 1, right? So it becomes minus. And now I will rewrite this one. So I have plus summation of alpha I plus C summation of sigma I minus summation of alpha I is minus summation of alpha I yi b minus summation of beta j sigma j. Right? So let's look at here. Summation of alpha I yi is 0. So this term is 0, right? Now, these two terms are the same thing. So we will get minus 1 over 2 of we have plus summation of alpha I. Now, I'm going to simplify these three terms. They all have summation of sigma I in common, correct? So I can write it as summation of sigma I times C minus alpha I times beta J. What do we know about that?
0.
It's 0. So all those three together goes 0, correct? So we have we looked at that one there. We are trying to maximize for alpha minus 1 over 2 summation I from 1 to j from 1 to alpha j I j x I transpose xj plus summation of alpha I subjected to, remember in the previous example, in a hard margin SVM, I said that you need to add those constraints. If you use something here, those findings, they should be the constraints. So we say the first thing is that summation of alpha I yi should be 0. That's one thing. Then we said C minus alpha I minus beta j should be also 0. We also know that alpha I should be greater than or equal 0, beta j should be greater than or equal 0. Those are something that we need to enforce basically. These two we already had, alpha I and beta j. These two we found and we use them here. So we basically enforce it as part of the constraint. We are solving for that, but we need to be sure we have this. Okay. Now, let's look at one thing here. Look at this optimization that we are doing. So we are maximizing this objective function with respect to what? Alpha. Because alpha is the only unknown remain, right? But when you are looking at your constraints, we have beta still. So beta is not a parameter that we learn for, but is in our constraints, correct? So let's see if we can get rid of that. Because we don't solve for it. Why should we have a constraint over something that we are not solving for it, right? So let's look at here. So we are saying that alpha I is greater than or equal 0. Beta j is greater than or equal 0, right? We also say C minus alpha I minus beta j is 0. So we want to get rid of beta, right? Beta has two scenarios. It's either greater than 0 or 0, right? So let's assume beta is 0. And then next time assume beta is greater than 0. If beta is 0, what do you say about here? C equal alpha I. Okay. If beta is greater than 0, what would you say? What's the relationship between alpha and C? If beta is greater than 0.
Minus of C minus.
What was that?
Minus of C minus alpha.
Mm,
Because
Then
beta
C
J
minus alpha I has to be beta J.
no, beta J is greater than 0.
Then the term should be less.
Which one?
C minus alpha. No, then that term should be
No,
equal
what's
to.
the relationship between alpha and C?
E should be greater than
C should be greater than alpha. Right? That means alpha should be less than C. So C should be greater than. If beta is greater than 0, that means C should be greater than alpha. Doesn't matter what is the alpha. Correct? So that means from these two, I learned one thing. Alpha I is always less than equal C. Correct? I don't need beta anymore. I know whatever is beta gives me the two things. One is alpha is equal C, one is alpha is less than C. So in general, is alpha is less than equal C. Right? So we will pick that. So we're trying to maximize with respect to alpha. Subjected to. So we have summation of alpha I by I to be 0. But now all of this two together gave us one thing, that alpha I and should be less than equal C. Correct? Now what does this together gives you? Alpha I is greater than 0, less than equal C. So we have alpha I less than C, greater than equal to correct? So how many parameters do you have here now? Unknown parameters.
2n.
What are the parameters? C is not parameter.
N plus 1.
C is a hyperparameter. Remember, like a regularization?
N plus 1.
What is N?
N is like this second one.
So what are parameters, not constraints? Unknown parameters. How many parameters do you need to learn?
2n.
Which parameter you need to learn? Okay, so how many alpha you have? N alpha.
N plus 1 alpha, right?
Why?
Because like the summation term.
That's constraints. I'm talking about parameters.
Okay.
Unknown parameters. So we have N, which is alphas. You have N alphas basically. Now, how many constraints you have? N plus, no. How many constraints? Wait, actually, now you. So now let's break this down. Someone tells me, how many constraints do you see here? 2n plus 1. Why? There's 1, right?
One.
This is repeating n time. This repeats n time. N time alpha is greater than 0. N time alpha is less than C. So you have 2n plus 1. So we went from a D plus.
Is this right?
Wait, right here. No, that's not that one.
Oh, yeah, yeah.
Where was it? Oh, yeah. What was the number? D plus n plus 1 and 2n constraints. We went to n parameters and we just add one additional constraints, right? Now, let's look at here. On the right corner, we have the dual form of hard margin SVM. This is a dual form of hard margin SVM. This is a dual form of soft margin SVM. What do you see is the difference?
The constraint.
I'll give the second constraint.
Which part? less than equals C. The only additional term is here. So the only difference between a hard margin SVM and a soft margin SVM is that you put a cap on the value of alpha. Alpha cannot be greater than C. C is the regularization or the penalty basically that you define, regularization term, right? You define it as like a hyperparameter and say that if C, for example, I select C5 for my problem, and model is only allows to basically select alphas that are less than equal to 5. That's the only difference. By simply doing this, your problem from hard margin goes to a soft margin problem. Is that clear? Yes. All right, so now when you get to this point, again, same thing repeats. Now the only unknown is alphas. This is a quadratic programming again, and you either solve, you need to do solving some sequential algorithms, right? So we either do coordinate ascent descent depending on maximization, minimization, or you do something like SMO. But there are other techniques also. All of them, basically all these algorithms out there, they're focusing on how to optimize this learning. Because the learning in general is a fool. It's just, there's so many unknowns, you try to solve them. If you change one of them, it has impact on the other one. So all the algorithms that exist, they try to optimize the speed of this process. They all focus on the same thing, finding these alphas in some sort of iterative manner, right? So we are not going to go over that again, because again, it's either coordinate ascent descent or SM. So, but if you want to solve it, remember you need to use this, something like this, and that to solve it. Fix all the alphas, randomly initialize all the alphas, step 1. Step 2, keep n-1 fixed, solve for the other one. Replace it back, solve for the second one. As a loop, right? So if we basically write, when we code it, we will see that we basically write that as a loop to basically repeat this process, yes.
So let's say we have like a test set, like an X test and a Y test, then how would we like plug it into this form?
So we haven't solved yet.
Yeah.
This is not a solved problem. You need to solve this, find the alphas first.
Okay.
After you found the alpha, what do we know about? I removed it. What did we know about W? W equals summation of, let me rewrite it here. We just solved, remember? W equals summation of alpha I, y I, x I. When you find alpha, then you find W. And B is 1/2 mean of group 1 minus max of group minus 1. That's B. So you have W and B. Then for every new data point, every new test data point, all you need to do is replace the point in the line, see if it's a positive or negative. So W transpose, W star transpose X test plus B star is either a positive or a negative. You put a sign function behind it. If it's positive, returns +1. If it's negative, returns -1. That becomes a prediction, right? So now, we want to break this down. We assume that we have the alphas, right? We have the alpha, we have W, we have B. Now we want to see that if the answers that we have first, does it make sense? Is it correct based on the conditions? Also to break it down to understand for every data point on the chart, what are the findings? What's the meaning of the findings that we have? So we have this, let's call this and this. So I will try to we try to have not many points here so it's not confusing. So among the KKT condition, first one was stationarity. That means you should be able to take a derivation of L with respect to the original parameters and set it to 0, which we did. We took a derivation of L with respect to W, with respect to B, with respect to sigma. And then whatever we found, we replaced it back into L, and then we solved for Lagrange parameters, which is alpha and beta, correct? So the first one is proven, we proved it. We were able to take a derivation. The second one was primal feasibility. That means if you take a derivation of L with respect to Lagrange multiplier, if it's an equality, should become 0. If it's inequality, should be less than equal 0. We had two inequalities, alpha and beta. If we take a derivation of this with respect to alpha, what do you get? You get this, right? So this was less than equal 0, which is proven. If we take a derivation with respect to beta, what do we get? You get this, which is minus sigma, which is less than equal 0. So that is also proven. Third one was dual feasibility. Dual feasibility was saying that this and this should be positive, right? So we have, which we already said that. So alpha I greater than 0, beta j greater than 0, right? So let me actually add the other one here. So we have front of our eyes. So we said 1 minus sigma I minus yi W transpose xi plus b is less than equal to 0. Also minus summation of sigma j is less than equal to 0. So that was the primal feasibility, dual feasibility, right? Now the important one, the last one, was complementary slackness. Again, what does it tell you? Lagrange multiplier time constraints equal to 0. So let's complementary slackness. So it tells you two things. One is, I'm going to write the original here. Alpha I times this should be 0. The other one is that beta j times this, which is this term, should be 0. Right? Or you can do it. Summation, beta j, sigma j. This means individual also should be equal to 0. Actually, let's write individual so you don't get confused. That should be 0, that should be 0. Now, when I'm looking at these two complementary slackness conditions that they have, so when we solved for this problem, soft margin SVM, what is the remaining parameters that you're learning for? Alpha. C is the fixed number, hyperparameter. The only unknown here is alpha, right? We got rid of beta. Remember? So now when I'm looking at this, I'm going to use this as my main because alpha is there. Then I will go over this because I didn't solve for beta, right? So let's just start with that one. We know alpha is positive, greater than or equal to 0. So let's just start with case number 1. What if alpha I is greater than 0? So if alpha is greater than 0, what happens to this? Should be 0, right? So 1 minus sigma I minus yi should be 0. Okay. So now we go to second part. Okay. A. Now, what if beta let's say, what if beta j is greater than 0? If beta j is greater than 0, sigma is
Zero.
0, because that's the multiplication should be 0, correct? So, and the second scenario is that this is sigma j is greater than 0, then beta j is 0. Remember, sigma by default also was positive, right? That slack variable. Right, so it's either 0 or 1. Now let's see what will happen. So what did we learn before? We also learned C minus alpha I minus beta j equal to 0. So if beta j is greater than 0, what does that tell you about alpha I?
Will be less than C.
Is less than C, right? We have that. So that means alpha I is alpha star is less than C. So star, I put it a star, that means we solved for this, right? If beta j is 0, alpha I is
Equal to C.
equal to C. Now, so this is the second part. Now let's put this back here. 1 minus sigma I minus yi, right? So let's start with this one. Sigma j is 0. If you put it here as 0, this becomes yi w transpose xi plus b equal to 1. Correct? This equation, if this is 0, is equal to 1. Correct? Now, if this is greater than 0, you basically get yi w transpose xi plus b equal 1 minus sigma. Okay. Does that make sense? So now let's connect those here. Which points do you think 1A refers to? Exactly on the line. This. So this point will have beta j of greater than 0, sigma j of 0, alpha or j or I doesn't matter, less than C, greater than 0, greater than 0, less than C. Same thing for this point, so I'm going to just connect those. Correct? So this are support vector points. Support vector points. Any points on the decision boundary. Now, let's go to the second scenario. Alpha I is greater than 0. Beta j is 0. This is 1 minus this, and sigma is also greater than 0. Which point do you think this refers to?
This class.
These classified points. So, basically any points here, here, basically here's, and this point. Any point that is not on the correct, not on the line, or not on the correct side. They're either misclassified or they are within the margin. Okay, so they will get sigma I greater than 0, beta j is 0, alpha I, it's exactly C, and yeah. So this is important point, the alpha that you get for those points is exactly equal to C. It's constant among all of those. Right. So think about it. When you solve for SVM, at the end of the solution, you have a vector of alphas, right? Later, try at home, like before we code it, try it with SVM, scikit-learn. Solve it and get the alphas, vector of alpha after solution. The vector of alpha is going to be 0, 0, constant, something. The one that are constant, all the same, they're going to be misclassified point. So if your C is 10, you see some points that they have alpha exactly 10. Those points you could directly from alpha say these are the misclassified or points within the margin. Any other points that you get that like with that's not the same constant, then you say these are the support vector points. Okay. Now, so this is this scenario. Now let's go scenario number 2. What if this is less than 0? That means 1 minus y minus yi W transpose xi plus b is less than 0. If that's less than 0, that means alpha I should be 0. Correct? So here one scenario happens because if alpha is equal to 0, this is the part that we want to remember. If alpha I is 0, we know C minus alpha I minus beta G equals 0. So if alpha I is 0, what does mean about beta? Beta equal to C. So C minus alpha I minus beta J equals 0. That means C equal beta J, optimal line, right? If beta is C, what should be sigma? It doesn't have A and B because beta is fixed value, cannot be 0. So that means sigma is 0. Correct? Because C times beta should be 0. If beta is, beta times sigma should be 0. Right? Lagrange multiplier times constant should be 0. If beta is C, you don't have any other alternative for sigma. Sigma should be 0. Right? So, if this is 0, let's go here now. That means this distance becomes yi W transpose xi plus b. It's going to be greater than 1. Which points are those? All points that are correctly are on the correct side of the line. Right? Any of this point, basically, this and this. All the correctly classified points on the correct side of the line, not the decision margin, not within also. Right? So just exactly outside. So these points they have alpha I is 0, sigma is 0, beta is equal to C. Is this clear? Right. So I leave it to you to review it again. There are lots here to digest. Review it one time, but the concept behind this SVM is basically this. You try to basically find some alphas. If you have the alphas, you have your W's, right? And then the whole idea will be to find an optimal line that has the maximum separation from both classes, right? If you want to allow for misclassification, you go for soft margin. All you need to do is that basically add a C here. If you remove that C, it becomes hard margin SVM, no misclassification allowed. And at the end, when you solve SVM, you get these values, alpha, betas, and sigmas, right? Based on that, you can make a call that what is what. So that's the interpretation part. So if I know this combination becomes correctly classified, so I put this in as part of my code. If this happened, correct classify. If this happened in the wrong side or misclassified. If this happened, I would say that is a support vector point. Now, also for this one, we can break it down further. If sigma is more than 1, we know that's a misclassified. if sigma is less than 1, we know it's correctly classified, but is inside of the margin. Remember at the beginning when we defined the sigma, the slack variables? We said if your point falls in the margin, but on the right side, like a correct side, the sigma is between 0 and 1. If it falls on the wrong side, is misclassified, then sigma is greater than 1. Here we said sigma is greater than 0. So you can put another step, check. If the sigma was more than 1, misclassified. Less than 1, correctly classified, but within the margin region. Okay. All right. So we'll stop here.